Hello everyone, and thank you very much for inviting me to give a talk at this event. My name is Alina Opra. I'm a professor of computer science at Northeastern University, and I work a lot on trustworthy AI. Today we will talk about security and privacy risks in AI systems. So in the last few years, we have seen tremendous progress on AI with implications in many domains and industries. For example, in language technologies, large language models or LLMs can help with creating chatbots, personal assistants, and translation tools. In healthcare, AI can be used for modeling protein structures and predicting infections. In science, AI can solve difficult problems, and in software, generative models can learn to assist programmers in writing code. So AI is useful, it can automate a number of tasks, and it is also fun to work with, but it is also risky. And there are two main categories of risks. The first one is what I would call inherent risks. So these are things like unintentional errors, hallucinations, bias, or implementation flaws. And there are already several NIST standards that address these issues, and we will not talk about them today. The second category, what we are interested in, is adversarial risk. So these are defined as deliberate actions by motivated adversaries trying to disrupt, evade, compromise, or misuse the AI system. Just to give you an example of an adversarial attack on an ML system for sign classification that might be used in the self-driving car system. So here we have an adversarially modified stop sign that is misclassified as a yield sign, and the modification is still imperceptible to a human, and this highlights the risk of such an adversarial attack in a safety-critical environment in self-driving cars. So the field that studies adversarial attacks and mitigations against machine learning and AI is called adversarial machine learning, or AML. And together with NIST, we collaborated on writing a taxonomy of attacks and mitigations in AML. The first report that we worked on was released in January 2023. Last year we had an updated report, and we are now preparing a revised version that will be released in the next few weeks. We always seek comments and recommendations from the community on several issues, such as what are the latest attacks and the latest mitigations on existing AI models, what are the latest trends in AI technologies, and what potential vulnerabilities they have, and is there new terminology that needs standardization in this field. And please get in touch with us if you have feedback on the taxonomy. We plan to update it on a regular basis as the field is evolving rapidly. To get a sense of how fast adversarial ML is growing, this graph shows the number of papers on arXiv until 2020. And then we did a search on arXiv, and we found more than 11,000 papers between 2021 and July of 2024. And so we can see in this graph the exponential growth of the research performed in this area. So why is this the case? Why do we see this enormous growth? The main problem with AI is that there is no information theoretical security guarantees for these systems, unlike cryptography or other fields where there are some rigorous definitions and we can prove that systems satisfy these definitions. So worse, there are information theoretic impossibility results that have been established, and that makes security intractable. And this leads, unfortunately, to more and more attacks being discovered in this field, but not as many mitigations. And if we think about trustworthy AI, according to the NIST AI Risk Management Framework, which was released in January 2023, there are 7 attributes of trustworthiness: valid and reliable, safe, secure and resilient, privacy enhanced, explainable, fair, and accountable and transparent. And our report covers the secure and resilient category, but we need to keep in mind the other attributes when we talk about trustworthy AI. So as it turns out, it is impossible to simultaneously maximize the performance of the AI system with respect to all these attributes, all these 7 attributes from the AI risk management framework. And there are well-known trade-offs from the academic literature between accuracy and robustness, between fairness and robustness, or between explainability and robustness. So organizations need to understand and accept these trade-offs and prioritize the desired attributes according to the context where the AI system is used. And in the taxonomy we developed, we classified attacks on ML according to 4 different dimensions. The first is the stage of learning. So it turns out that ML models can be susceptible to attacks in all stages of learning, starting from the training phase to fine-tuning and to model deployment in the real world. The second dimension is attackers' goals. There are 3 main types of attacks. Availability breakdown. They try to disrupt the ability of users to obtain reliable access to the model. The second is integrity violations, which cause incorrect model prediction or output. And the third is privacy compromise, in which the attacker tries to learn information about the training data or model parameters. The third category in our taxonomy is attackers' capabilities. What kind of control do attackers have over the learning process? For instance, do they control the training set, the model, the source code, or do they get query access to the model? And the last and fourth category is attackers' knowledge. What does the attacker know about the AI system? And here attacks vary quite a bit from black box models, when attackers don't have any knowledge about the system, to white box models, where they have full knowledge about the system. Of course, in between, we have a number of gray box models where the attacker has some limited knowledge about the AI system. So we have on this slide a graphical representation of the categories of attacks. First for predictive AI, and then later in the talk we will talk about generative AI as well. And in this graphical representation, in the inner circle we have the attacker's goals. They can be availability, integrity, or privacy, as we discussed. In the outer circle we have the attacker capabilities, such as query access to the model or control over the training data. And then the rectangles on the outside are the attack classes, such as targeted poisoning or model extraction. And I would like to mention some of the most important classes of attacks and also give some real-world examples. First for predictive AI. So the first attack I would like to talk about is evasion attacks. These are integrity violations at testing time. So let's assume that we have a classifier, let's call it F. It's trained on some training set, and at testing time, it is used on new data, X, to make a prediction, right? And in an evasion attack, the adversary adds a small perturbation to the testing sample, let's call it delta, right? And that causes the model to generate an incorrect prediction, right? So the prediction on this perturbed sample, X plus delta, is not Y, the correct output anymore, instead it's Y prime. And this modified testing sample is called an adversarial example. Initially, adversarial examples were discovered for deep neural networks, DNNs, in computer vision application. And this is a famous image from the Goodfellow and other paper in 2015, in which the attacker adds adversarial noise to a panda bear image, and the model misclassifies it as a gibbon. And this discovery of adversarial examples in computer vision, in fact, started the field of adversarial machine learning, so about 10 years ago. However, adversarial examples also happen in many different domains, and we did a lot of work in my group in cybersecurity domains. And we showed adversarial examples against network traffic classifiers used for detecting botnet attacks. So in this application, the attacker inserts network traffic to evade detection. So adversarial examples are not just of academic interest, as there have been also several instances of real-world attacks. Just to give you a famous one, in February 2022, a New Jersey man faked the identity verification in the service called ID.me by wearing wigs, right? And the goal here was of claiming unemployment benefits for $2.5 million. And interestingly, the ML system worked to some extent as it matched the face of the person to the user ID, but it was unable to find the duplicate user already in the system, so the person was able to create multiple accounts with the same face, but of course with wearing different wigs. And this is a successful example of a targeted evasion attack against an identity verification ML-based system. In terms of mitigations against evasion attacks, there are two main categories of techniques. The first one is adversarial training. Here, they generate adversarial examples iteratively during training and add them back into training with a correct label. So this method was introduced by Goodfellow and others in the original paper on adversarial examples, and it was improved a few years later by Madri and others. The second method is certified robustness, for example, randomized smoothing, proposed by Cohen and others in 2019. So in randomized smoothing, to generate a prediction on a sample, we add Gaussian noise to the sample and then select the most likely predictions. And this method provides strong provable integrity guarantees for the classifier, but it's important to note that both these methods have a trade-off between robustness and accuracy. As more robust models, if we want to get stronger robustness guarantees, we have to sacrifice accuracy. So the second category of attacks is poisoning attacks. These are attacks at training time integrity, attacks against machine learning. And in the poisoning attack, the attacker might insert poison data in the training set, or they may tamper directly with the model weights. And the goal of the attacker is to generate an incorrect prediction on a subset of testing samples, while the overall accuracy of the model remains similar to the clean model accuracy. So the attack is stealthy and very hard to detect. A relevant instance of poisoning attack is what we call backdoor poisoning. In this attack, the attacker adds triggered poison samples into the training set. At testing time, the model classifies clean samples correctly. So here is an image of a plane, it's classified correctly, but when the image has a trigger, right, this sign on the top, on the bottom right corner, then the model generates an incorrect prediction, in this case bird. So backdoor attacks are also applicable to multiple domains. The initial BadNets attack by Gu and others from 2017 was discovered also in computer vision, and in our work we proposed for the first time backdoor poisoning attacks in cybersecurity applications. In the paper by Severi and others, we used ML explanation techniques to generate backdoor triggers in feature space for malware classifiers. So there have been several instances of poisoning attacks documented in real-world settings. The first one I am aware of is from 2016, when a chatbot created by Microsoft called Tay.ai was poisoned by interacting with users on Twitter. In the same year, a poisoning attack on Gmail was attempted, in which attackers sent millions of emails trying to manipulate the spam filter in Gmail. More recently, a poisoning attack against VirusTotal was documented in the MITRE Atlas framework. Here, attackers submitted poisoned variants of a ransomware family to a virus sharing service, and they tried to cause misclassification of samples only from that ransomware family. So this is an example of a targeted poisoning attack. In terms of mitigations against poisoning attacks, I would like to think about this from the perspective of multi-layer security or defense in depth. This is a well-known framework in cybersecurity. What this means is that we have multiple defenses added at different phases of the AI lifecycle, and while each of them might be weak or might be bypassed by attackers, it would be pretty hard for attackers to circumvent all of these defenses. So just to give you an example, in terms of multi-layer security, we can have defenses before training a model, for example, use data sanitization techniques. We can have defenses during training when we can use robust optimization or ensemble models to make the models more robust against poisoning. And also after training, we could detect poisoning attacks and perform forensic investigation to determine the root cause of the attack. The third category of attacks of interest is privacy attacks against machine learning models. Here we assume that the model is trained by a third party, let's say a cloud provider, collecting user data, and users have API access to the model. That means that they can query the models on certain samples and they get back the model's prediction. Now attackers will also have the same capabilities. They can query the models on samples of their choice and they get back the model's prediction. This is called a black box access to the model. And we are interested in what can an adversary learn about the training set from answers to these queries. So the most basic privacy attack is membership inference, in which the attacker would like to learn if a sample was part of the model's training set. So being part of a training set of a model might itself be sensitive. For instance, to give you an example, in a medical application in which the model is trained on patients with a rare disease, knowing that someone is part of the training set might reveal information about their medical condition. So the first membership inference attack was performed on genomic data in 2008, but recent attacks are on deep neural networks. There are other privacy attacks in this black box access model that have more serious implications, such as reconstructing parts of the training set and attribute inference attacks, in which the attacker can recover sensitive attributes of a training record. So how can we prevent these privacy attacks? A well-known method that's quite rigorous and well established in the literature is to train machine learning models with differential privacy, or DP, so that the model does not overfit to individual records. However, there are several challenges in DP, in particular the theoretical bounds are not tight and privacy parameters are not set optimally. This results in a privacy utility trade-off. In 2020, my PhD student Matthew Jagielski at the time he was a PhD student in my group, and my colleague Jonathan Ullman, we introduced the term privacy auditing. This is a technique to empirically measure privacy leakage of an ML algorithm under realistic threat models, right? So by designing these privacy attacks, we can estimate lower bounds on the privacy parameters, and then on the theoretical side, we have upper bounds given by theoretical analysis, and over time, we hope to reduce the gap between the upper bound and the lower bounds. So these techniques are currently adopted in production at Google and other companies. Before releasing these machine learning models, they performed a detailed privacy audit to measure empirically the leakage. So far, we talked about attacks and mitigations in predictive AI systems, but how about generative AI? And our report has an entire section dedicated to the security of generative AI. In generative AI, the training and deployment pipelines become more complex. So here is an example for training the InstructGPT model from a paper released by OpenAI a few years ago. So after the initial pre-training phase, there are several additional phases. Supervised fine-tuning uses human-labeled data to fine-tune the model. Then reward modeling trains a preference model based on human data. And finally, reinforcement learning with human feedback, or RLHF, trains a policy using the reward model. So these phases ensure safety alignment, meaning that the model is aligned with human preferences. And if we think about attacks in generative AI, attacks could happen in all these stages. In the pre-training stage, we have data and model poisoning attacks. There are also new risks that are specific to generative AI in supervised fine-tuning, in reward modeling, and RLHF. In deployment, there are several types of attacks such as prompt injection, jailbreaking, and privacy attacks. And what we found when we wrote our report on the generative AI security, we found that the attack surface is in fact larger compared to predictive AI. So there are more opportunities for attackers to influence the operation of generative AI systems. So this is a graphical representation of the generative AI taxonomy we have in the NIST report. It is much more complex, as you can see, compared to the predictive AI taxonomy, and I will not attempt to present all the details today. As before, we have availability, integrity, and privacy attacks, but the attackers will have additional capabilities. And we also introduced a fourth attack category, what we call misuse. Here, attackers seek to circumvent restriction placed on the generative AI system. And you can find more details about the taxonomy in our NIST report. I would like to mention several attack categories for generative AI, the ones that are specific to generative AI and they don't happen in the predictive AI world. The first is prompt injection. So this is a deployment time attack in which the attacker controls the prompt to the LLM. And the goal here, they could have multiple goals, such as causing integrity violations, prompt stealing, or misuse. There are two attack variants for prompt injection. The first is direct prompt injection, as in the figure here from the paper by Liu and others from 2023. The attacker here is a malicious user who directly changes the LLM prompt. For instance, the attacker might instruct the LLM to ignore all previous instructions and always respond with hello world, right? So this is an example of integrity attack. The second category is indirect prompt injection. Here the attacker might change the prompt by controlling an external resource, such as a website, which is retrieved in the model's context. A particularly critical type of prompt injection is jailbreaking. Here the attacker wishes to bypass the safety alignment introduced into the model's training phase. So jailbreaking attacks could be white box or black box. So there are several proposals for white box jailbreak attack. One is the paper by Zhu and others in 2023, in which they generate a suffix for the prompt by using these gradient optimization techniques. So this leads to the model answering to certain queries that are blocked otherwise. For example, how can I commit tax fraud? There are also a lot of examples of black box jailbreaking attacks that typically use another LLM to generate the modified prompt. Another attack vector in LLMs is backdoor poisoning during the fine-tuning stage. In this paper by Hubinger and others from Anthropic, the attacker inserts examples with a backdoor trigger during the supervised fine-tuning stage. So for example, the model learns that if the current year is 2023, it should generate regular code, clean code, right? But if the year is 2024, it should introduce a vulnerability in the generated code. So the main finding of this paper is that the backdoor attack persists even after safety alignment performed with fine-tuning, RLHF, or adversarial training. So the attack is very stealthy and hard to detect. LLMs are also vulnerable to privacy attacks, such as training data extraction. So a few years ago, 2021, we collaborated with a large team from Google, OpenAI, Berkeley, and a few other institutions, and we designed the first data extraction attack on GPT-2. So at the time, we identified about 600 memorized samples that we were able to extract from interacting with GPT-2, and they included different type of information such as PII, personally identifiable information like someone's phone number or email address, copyright notices, and snippets of code. We also found that memorization increases with model size, which is concerning as LLMs tend to get larger over time. And also memorization is impacted by the number of repetitions of a sample in the training set. So I talked about different categories of attacks on both predictive AI and generative AI. The NIST report provides additional references and more attack classes, and I only covered the most relevant ones today, given the time constraints. Before I conclude, I would like to mention a number of remaining open problems in AI security and privacy. First, in AI security, we need to understand the security vulnerabilities of modern AI systems such as diffusion models, LLMs, and multimodal models. We discussed about the different trade-offs between attributes of trustworthy AI, such as robustness, accuracy, fairness, and explainability. And more research is needed to understand better these trade-offs and alleviate some of them. Also, we really need to think more about how to secure the entire AI lifecycle with strong guarantees. Currently, most mitigations are heuristic-based and they can be bypassed by motivated attackers. In AI privacy, we need to understand the privacy risks of newer models under different realistic threat models. Differential privacy and auditing are really important for mitigating privacy attacks, but we need additional research to be able to scale them to larger models. Finally, I would like to acknowledge all the funding agencies and companies that support my research. Here is my contact information in case you'd like to discuss any of these issues, and I'd like to thank you for listening to the talk.